in the last lecture we have started network theorem, where we have discussed superposition theorem, and we have also discussed about an ideal source, voltage source and current source. And today we'll start with reciprocity theorem. According to the reciprocity theorem, we know that in a linear network theorem, linear network with linear and bilateral elements and a single voltage or current source, the current in one mesh is equal to the current in the latter when the same EMF is placed in the former with its impedance. So this is what we need to know about the reciprocity theorem. So now what we can see is that we'll consider two mesh network over here. You can see in the already I have drawn it over here. It's a two mesh network, with the current I1 in the first mesh and the I2 in the second mesh, and the equivalent of it has been drawn over here. Here we have just replaced this EMF we have placed over here, and the impedance, it is over here, right, Z0, and the other thing is same. Here we have assumed the current to be I1 prime and I2 prime. Now applying the Kirchoff's law to the meshes, when the voltage source in the first mesh, we'll just write down the equation using the the Kirchoff's law. What we'll write is that E is equal to, we'll just consider this one, the first mesh. So E will be equal to Z1 plus Z0 plus Z3 into I1, and minus Z3 into I2. So this is the first one, this loop, and then for the second loop the EMF is over in this mesh, actually it's 0 is equal to minus Z3 I1 plus Z2 plus Z3 into I2. So what we do is that we'll try to solve this one with the help of Cramer's source or Maxwell's method to get this value of I2 as Z3 into E, and this will be divided by Z1 plus Z0. Z1 plus Z0 into Z2 plus Z3 plus Z2 Z3. So this what we'll write, and similarly we'll just look into this mesh. Again we'll try to solve this. We'll again use the Kirchoff's law, and we'll write for the first loop, this part we'll write 0 equal to Z1 plus Z0 plus Z3 into I1 prime minus Z3 into I2 prime. And for this loop, the second loop, E will be equal to minus Z3 I1 prime plus Z2 plus Z3 into I2 prime. So again solving for I1 prime, with the help of again Maxwell's method or Cramer's rule, we'll get I1 prime equal to Z3E divided by Z1 plus Z0 into Z2 plus Z3 plus Z2 plus Z3. That's what we can see over here is that I2 equal to I1 prime, as required by the reciprocity theorem, which is already we have just read out over here what actual reciprocity theorem is all about. So we just have proved this I2 equal to I1 prime, which is actually the proof, or which is the condition required by the reciprocity theorem. That is, the ratio of EMF in one mesh or branch to the current in other mesh or branch is called the transfer impedance and represented by ZTR. So that will be it's a part of it, but then the actual thing is that we just need to prove this I2 equal to I1 prime. That is what we have done. Then coming back to Thevenin's theorem. As Thevenin's theorem, what we know is that this is the third one. Now according to Thevenin's theorem, any two terminals, again just see over here, any two terminals linear network containing voltage source and the impedance may be replaced with an equivalent circuit consisting of voltage source E0 in series with an impedance Z0. E0 is the open circuit voltage between the terminals, and Z0 is the impedance across the terminals when all the voltage sources have been replaced by their internal impedance. Now this is the Thevenins and the Nortons, which we'll discuss ahead. These are the basic two theorem which is very much required to solve the complicated circuit. So we'll just focus on this one, on Thevenin's theorem rather. As per the Thevenins, we've just drawn this circuit. Okay, here you can see the EMF E over here. Here the current is I in this loop and I2 in this loop. So we'll just saw the direction of the current over here. Okay, now it's okay. Now this is the equivalent. This is the equivalent Thevenin circuit which we have drawn over here. So here the circuit in this two terminal, I mean the circuit containing two mesh, we have Z1, Z2, ZL, load resistance obviously. Here this is the terminals A and B, about which we need to know the voltage. So we'll again this is I1 over here, I2 over here, and Zi is the internal impedance of E over here. Okay, now we have just considered two terminal network. Okay, one active, this one is an active, other one is the passive one. If we have just placed this load impedance over here, then the mesh, writing the mesh equations again using Kirchoff's law, we get for this one, for the first mesh, we'll write E equal to Z1 plus Z3 plus Zi into I1 minus Z3 into I2, and over here we'll write 0 equal to, for this loop, for this mesh rather, minus Z3 into I1 plus Z2 plus Z3 plus ZL into I2. So we'll solve for I2. We'll solve it for I2. Again using Maxwell's method or by Cramer's rule, we can find out the value of I2 as I2 equal to Z1 plus Z3 plus Zi. This one. Okay. Again E and Z1, Z3, Zi. And then we'll write minus Z3. Okay. And E and 0. Okay, this is for I2, we'll just put E and 0 in the place of the coefficient of I2 divided by mod of Z, that is Z1, Z3, Zi, and here it's minus Z3, then again minus Z3, and then we'll have Z2 plus Z3 plus ZL here. So we'll get the value of I2, and it can be written like this: E Z3, I'm just modifying it, E Z3 divided by Z1 plus Z2, rather Z3, Z1 plus Z3 plus Zi whole divided by Z2 plus ZL plus Z3 into Z1 plus Zi whole divided by Z1 plus Z3 plus Zi. So this is the value for I2. Now what we need to do is that we'll just have to see how we can use this particular circuit. So before moving ahead, we need to find out E0 and Z0. Okay, so E0, how to find the E0? Okay, so you have to see that to find out the E0, we need to know that the we need to find out the open circuit voltage across this two terminal AB. Okay, so if an open circuit, what you'll do is that if there is no ZL over here, okay, you'll get the EMF, that is E0 equal to, it will be given by E into Z3 divided by Z1 plus Z3 plus Zi. Okay, similarly to find out the value of Z0, again this Z0, okay, this Z0 can be obtained. How it can be obtained? Z0, okay, So to find out, this is the basically total impedance, okay, between again the terminals A and B, or here you can say A and B. Okay, we'll just remove this one. We'll have Zi over here. So Zi, Zi and Z1 will be in series, which is in parallel with Z3, and this whole thing is in series with Z2. So that you'll have to see. Okay, so Z1 in series parallel to Z3, which is in series with Z2. That will give the equivalent impedance across the terminals AB. So this will be Z0 equal to Z2 plus 1 divided by 1 by Z3 plus 1 by Z1 plus Zi. So this will be equal to, so this is how much you'll get. This will be equal to Z2 plus Z3 into Z1 plus Zi. Okay, and this thing divided by Z1 plus Zi plus Z3. Now E0 and Z0, here E0 and Z0 are called Thevenin's component. This is known as Thevenin's component. Thevenin's component. Okay, so again, focusing on this circuit, we can write the current over there. If it is I2, so again we can write I2 over there. I2 will be equal to E0 divided by Z0 plus ZL. Substituting the value of E0 and Z0, which we already have. Here we have E0 and here we have Z0. If you substitute the value in this particular equation, you are going to get the same value. This I2 will be similar to this I2. Okay, so this confirm the same current is obtained. Okay, and this has been, or this is known as a Thevenin equivalent circuit. So this circuit will be termed as a Thevenin equivalent circuit, equivalent of this circuit. So this circuit can be redrawn and can be Thevenized as this. So we have just discussed about the reciprocity theorem and Thevenin's theorem. In the next lecture, we'll discuss about again the Norton theorem and the maximum power transfer theorem, with which after that we'll come to the end of this network theorems. Thank you.